In this video, we're going to start discussing Principal Components Analysis, or PCA. This is an advanced solution for dimensionality reduction and is very commonly used. Essentially, PCA is a technique that reduces the number of features while keeping as much information as possible by finding the principal components. These are the directions along which the data varies the most. So first, we need to figure out what the direction that data varies the most actually means. Let's revisit this example. This time, the question we need to consider is, in which direction does the data vary the most? To help you understand, I've drawn a Cartesian coordinate system to represent the dataset. The x-axis represents humanities scores, and the y-axis represents science scores. Each data point is plotted in this space based on its scores, showing its position in the feature space. If the dataset had 3 features, we'd use a 3-dimensional coordinate system, and within features, it would be an n-dimensional space. Based on this figure, take another look at the question, which direction does the data vary the most? First, we should try to identify some directions in the coordinate system. I think there are 2 obvious directions, the horizontal axis and the vertical axis. If we use the horizontal axis as our direction, we are effectively projecting the data points onto that axis, which gives us the original humanities scores. Similarly, projecting onto the vertical axis gives us the original science scores. Based on our earlier discussion, we already know that science is a better feature than humanities. In other words, in this example, the vertical axis is a better direction because it yields a dataset with greater variance. So, do you think the vertical axis is the best direction? Remember, our goal is to find the direction in which the data varies the most, so that when we project the data points onto that direction, we get a low-dimensional dataset that retains as much variance as possible. If you haven't yet figured out under which conditions the projection yields the maximum variance, take a look at the image with 3 different lighting conditions. Which one results in the projection points being the farthest from the origin? The answer is that the projection along the 45-degree line gives the largest variance. That's because this direction is the closest to the line connecting the red data point to the origin. In theory, if we had a magenta option and could shine light perpendicular to the magenta direction, then the projection along the magenta direction would yield the maximum variance. Now, let's address the original example. If we can find a direction that roughly connects all the points, then by projecting the data points onto that direction, the new dataset will retain as much of the original variance as possible. So, the answer is shown in the last image. Even though not all data points fall exactly on the orange line when projected, this direction maximizes the connection between the points. As a result, when we project the data onto this direction, the new dataset retains most of the original variance. In other words, this orange direction represents the direction in which the data varies the most. In linear algebra, we have a specific term eigenvector to represent this direction. In this lesson, we won't spend too much time on the details of linear algebra or how to calculate eigenvectors, but I want you to understand the underlying concept and physical meaning here. For actually computing eigenvectors, you can simply use predefined functions and libraries. Now, let's walk through the step-by-step calculation for PCA. The first step is to normalize the given dataset. Since there are different methods of normalization, the numerical values in the normalized dataset might differ, and that's perfectly acceptable. Of course, if you use different normalization methods, the numerical values produced by PCA might not be identical, but that's quite common. Since this lesson doesn't require you to manually calculate eigenvectors, we can use Python's NumPy library to handle the intermediate steps. First, we compute the covariance matrix. Then, using the covariance matrix, we calculate the eigenvectors and eigenvalues. Finally, by multiplying the normalized data with the transformation matrix made up of the eigenvectors, we obtain the final principal components. Here, we present the results of each step in the calculation. If you'd like, you can write your own code and print out the values at each intermediate stage to compare. Although this lesson doesn't require you to manually compute eigenvectors and eigenvalues, we still expect you to understand their underlying logic and how to use them. We can stack the eigenvectors vertically to form a transformation matrix. By multiplying the normalized dataset with this transformation matrix, we obtain the dataset's projections onto the different directions. Finally, it's important to understand the physical meaning behind the eigenvalues here. Eigenvalues represent the amount of variance retained in the new dataset after projecting onto the corresponding eigenvector's direction. If we use all the dimensions in PCA, meaning we don't actually reduce the dimensionality, we keep all the variance. In other words, the sum of all the eigenvalues will equal the total variance of the original dataset. Therefore, we can calculate the proportion of the total variance that each eigenvalue represents, which is called the variance ratio for each component. Using this method, we can determine the relative importance of the new dataset produced by PCA. This ratio is a key reference for deciding how many dimensions to retain. For example, we might set a threshold of 90%, meaning we want to retain at least 90% of the variance after PCA. If the first principal component doesn't provide 90% of the variance, we add the second principal component, and so on, until we reach that threshold. It's important to note that we can't arbitrarily pick principal components, we always choose them in order from the largest variance to the smallest. Finally, let's take an overall look at the results of PCA. You can see that we only performed mathematical operations on the numerical values of the features throughout the process, without using any labels. In other words, PCA is an unsupervised technique because it doesn't require labels. That's our complete discussion on PCA for now. In the next video, we'll cover another common technique called linear discriminant analysis, and we'll also briefly discuss some of the disadvantages of PCA during the motivating analysis.